Today we're going to have a look at the third session. So third session is more or less following what we've been doing before. So now we're going to look at, first time we're going to look at control loop for digital controls. That means our controller is a digital controller. So it's working in discrete time. And our plant is in continuous time. So as I was just saying, we're going to look at the first control loop with a so-called digital controller. So it's exactly the same as in continuous time. The only difference is that here we're considering a digital controller. So a digital controller, you need to add two blocks, basically. So the first one is a sampler. The sampler is just taking one value here, so the input minus the feedback. And it's taking one value every t seconds. So capital T is our sampling time. And every capital T second, we're taking one value, feeding it to the discrete controller. And then this discrete controller is computing an input for our continuous time plant. And so the second block here, which is a zero order hold, I don't know if you remember it, we've already seen it before. It's just taking the value of the controller at times capital T, and it's just holding it for the input of the continuous time system. Here we will also consider the disturbance. The disturbance usually it's in continuous time. So here for this exercise, we just considered disturbance in the S domain or in the continuous T domain. So today we're going to look at first the plant reference transfer function. So how, if I know U of T, I can find Y of KT. We're going to look at the plant disturbance transfer function. So if I know the disturbance, how can I find the transfer function to find Y of KT with respect to this disturbance? And finally, we're going to look at the role of the sampling at the input. So mostly this block here. Why do we need this one? And if we don't have this one, if we directly consider here a continuous signal in our controller, a continuous output, and then a zero order hold, what's happening and why is it not possible? So let's first dive into the first exercise. So the first exercise is really important. It's really here to show you how the sampler or the sampling here is affecting the continuous time system, and why, if you had a sampler here, the continuous time system, which is 1 over S times this one, if you just split it basically with a sampler in between, it's not the same system anymore. So sampling is really affecting the dynamic of the system. In this case, we're going to see how the sampling is affecting our system. But remember that adding a sampler is changing the behavior of the output Z and even the output or the intermediate signal Y. So we're going to consider a sampling interval of 1 second, so sampling time of 1 second. And the first question is to find the relation between the output Z and the input X for each of these systems. So first of all, let's consider the first system. So with the first system, it's quite easy because what we want to find is the output Z with respect to the input. We will find Z first in the continuous domain. So in the continuous domain, we have G2 times GA1 times X star. And so here there's a problem that X star, you know that it's not easily possible to describe it into the S domain, at least with linear transfer function here doesn't exist. So we need to switch to the discrete representation. So in the discrete representation, we need to discretize our output Z. And so discretizing the output Z is equivalent to discretizing the G2 times G1 system. So we're discretizing the output of these combined two systems because in between it's continuous. So we cannot differentiate. We cannot say that the first system output is something, second is something, because they're strongly linked with here they're linked in continuous time, basically. So we can compute Z of Z, so Z in the discrete representation. So we have to Z transform this expression here, G2 times G1, and we need to consider X of Z. So X of Z is directly known, or it's not directly known, but it's the Z transform of X of S star. And so x of the star means that it's already discretized. So here, if we want to find the discrete transfer function of the system, the only thing we need to know is to z-transform these two blocks multiplied by one another. So we need to z-transform this. So we've already seen how to do it. First, we use the partial fraction expansion. So we say that this has two poles, one at 0 and one at minus 0.1. And then we find the two numerators. So you can do that in MATLAB. I'm going to show it once again in a couple of seconds. And so you end up with two fractions like this. Then when you have this, you know that using a table that is given here in the Formelsammlung, you can go here and you can directly identify that once again, you have this 1 over s plus a. So 1 over s plus a, you all know that it represents an exponentially decaying function. And we can identify this exponential minus 80 term into the discrete x of z representation, so discrete representation. So here we have 1 over 1 minus exponential minus, let's say, the first a kt times z minus 1. And here, as it's 1, we can say that's directly an integrator. So if I go back to the table here, when you have a equals 0 here, it's equivalent to having an exponential decay with no decay at all, which is just a step function, okay? So in continuous time, you have 1 over s, that's 1 over s plus a with a equals 0. And obviously in discrete time, you got 1 minus ez minus 1 here, because exponential of 0 is 1. So here you have two exponential decay. The first one is a step, and the second one is just an exponential decay with some decay factor here, 0.1 capital T. And so given that t is 1 second, you can plug in t into the equation, and then you can rewrite it a little bit differently. So you can just put the two fractions into the same denominator. And finally, you can also plug in all the values. So if you plug in all the values, you end up with this transfer function, which is first order on the top and second order on the bottom. And then we will now do the exact same analysis for the second system. So the difference for the second system is that we're adding a sampler here that is h0 hat. So I don't know why it's not written correctly, because so here the pen here, it should be h0 hat. It's not displayed correctly on the screen, but never mind. So this h0 hat is exactly the same as h0. It's a sampler. It's just to remember that these two samplers are not connected to one another. So it's just two of the same block, basically. So here, if we want to find the output C, we need to take the output of the G2 block, and the input of J2 is Y star. So that means that Z is J2 of S times Y of S star. So it's a discretized version of the output of J1. So then we can express what Y star is. So Y star, this signal here, is nothing else than the sample version of Y, and Y is the output of J1. So the output of J1 is J1 times X star, because it's X star the input. And so if we star everything, we have J1 star X star. So basically, this is already discrete. So if we discretize Y here, we're just discretizing the system times the discrete input directly. Then we can rewrite Z, so we just plug in Y. If we plug in Y, we have J2 times J1 star times X star, and we want to find the discrete version of it. So if we want to find the discrete version of it, once again, we just star everything. So we discretized everything here, and we end up with J2 star, J1 star, X star. So here's the main difference before with the system we've just seen before, is that because there's another sampler here, then J1 and J2 are not coupled anymore. So if I want to Z transform this expression to find the transfer function, so Z of Z is J2 times J1 times X, exactly the same as here, but in the Z domain. If I want to find the Z transform, I need to Z transform each term individually. So now I'm not Z transforming the J1 times J2, but I'm Z transforming J1 and J2 and then multiplying them to find the transfer function. So if we do exactly the same, it's exactly the same as before. We go in the table, we find that there's this term and this term. So step function and an exponential decay, we can find the equivalent x of z. It's exactly the same as for the first system, so the poles are exactly the same. And we can find the two numerators, and we can directly multiply these two fractions with one another to find a little bit of a compact form. We can also plug in t equals 1 second, and we end up with this expression here. Also, we may find the numerical application for this one, and we find this expression. So now, let's compare this first system and the second system. So let's clear everything here. So we have our first system. We found out that this is the expression for our first system. And now we found the second system. So remember the first system, here we got one sampler like this, then we got J1, and then we got J2, okay? For the second system, we got one sampler here, we've got J1, then we got another sampler, and then we got J2, okay? So this is the only difference between our two systems. We see the output, the input was X, and Y was in between. So now the question is, according to you, what difference can you expect for a step response? So if I do a step response for the first system here, and for the second system, just looking at these two transfer function, what can you expect as a difference? So for that, let me just launch a poll, which is this one. So can you all see the poll? And if you can see the poll, please answer, according to you, what should be the difference between the response, the step response of the first system and the second system? So basically, the idea is to understand what the difference, or what the fact that adding a sampler, how is it changing the system output? So can anyone say or use any functionality to tell me if the poll is working? And apparently it is, because I have now some answers.
It's working.
Okay. So it's a multiple choice polls. Once again, it's anonymous. And yeah, we'll just give you a couple of minutes to answer this one. So looks like it's not that clear which were the right or the correct answers. So the first answer was the second system output will show a higher static gain. Can anyone explain why this is true or wrong? Just as just to help you, this is true. So the first answer is true. Can anyone explain why is it true? Or did you just choose this answer and hope to be lucky enough that it was true? Or so this first answer was true. The second system output will show a higher static gain, and as we can see, it is first. You need to see that the two denominators, are identical. So the two denominators are exactly the same. Okay. So if I want to look at the static gain, I need to look at the numerator. And here I've got something to z-1. We know that z-1 is a unit delay. So that means that this one has one delay, or one sample time delay. This one has no delay. So this one will be a little bit later. Okay, it will be a little bit slower if you prefer, or more accurately, it will be shifted by one sampling time. And this will be not directly our static gain, because static gain is this divided by the sum of all the coefficients here, but at least the static gain is proportional to this value here and proportional to this value here. And as we can see, 0.1 is a little bit higher. That means that the first answer was, the first answer was right. So the second system will show a little bit of a higher static gain, okay? The ratio of the static gain will be 0.1 divided by this constant here. So it will be just a little bit higher. Then the second answer was the first system is one sample faster. So here it was a little bit, probably a little bit trickier, but indeed it's the opposite. Here you have something z minus 1. So that means that here, if I just retake z1, so just let me delete everything. It's not working. Delete, clear all drawings. Okay, so if I take this one, remember that I can put the denominator on this side, and I can say that this will be equal to z1 minus d1 k minus 1. This one will be evaluated at k plus 0.9 or almost 0.9 c of k minus 2. Okay, and on top I will have, so on the other side of the equation, I will have equals to 0.09 u of k minus 1. Okay, or x, sorry, it's x, so x of k minus 1. Whereas the second one, the numerator, so this part here will be exactly the same. So I can just rewrite this same expression here, and it will be equal to 0.9 times, sorry, it's still x of k, okay? Why is it x of k and x of k minus 1? This comes from this z minus 1. So here you got the z minus 1, and that is telling us that there's one sample delay, okay? Now, if we look at the third answer, both systems' output will have the same overall shape. So is it true or false? Here it's not that easy to answer, but the idea is you have exactly the same denominator, okay? So if you have exactly the same denominator, then the what's so-called the external behavior will be exactly the same. So imagine that both numerator are 1, for example. Then if I've got the same denominator, obviously the output will be exactly the same. Here, the only difference we will see in the output is because of the numerator. And here in the numerator, it's just a static gain, and here a static gain with a delay. So that means that both systems will show an overall exactly the same shape, unless the first one will be delayed by one sample and a little bit lower. So the gain will be a little bit lower. So this third answer was also correct. And the third one, if one system is stable, so will be the second. This is obviously also correct, because to know if a system is stable or not, we just look at the poles, or we just look at the root of the denominator, exactly the same as in continuous time. And here, if you look at the root of the first system, it's exactly the same as the second system, because it's exactly the same denominator. So just to summarize, both systems are behaving differently. They're not strictly speaking the same, but the same denominator means the same external dynamics. So the same pole location. Same pole location means the way the system is reacting to an input will be the same, but still the numerator is different. So the way the input is affecting the system is different. So to put it in a little bit differently, to say it differently, if you take these two systems, okay, and you set an initial condition that is not 0, then if the systems are stable, they will just go to 0 with only this dynamic will be used, because x will be 0. So 0 times this, we don't care of this. And so we only have this part of the equation that will be used. Then z1 and z2 will have exactly the same output. Exactly the same output because x is 0. If now we consider that both are at 0 at the beginning, so z1 and z2 are at 0, and we take any x value to just make an excitation of our system, then we can see that the numerator is different. And as the numerator is different here and there, then the output, overall output would be different. And so, as I just said before, the first system will show 1 time step delay, and it will be a little bit lower in the static gain. So if we just look, and that is the next question, if we look at the step response, so it's not really step response, it's step minus another step. So it's kind of a step only for the four first samples. Then you can see that as expected, the first system as one sample delay. So it's always later, I mean, the first here or the second sample is almost equivalent to the first sample of the second system and so on. So it's like the blue curve here is shifted to the right or the shifted to the left from the orange one. And the static gain, if we look at the end here, it looks like it's converging. There's this gap here, and this gap is because one is 0.1 on the numerator, orange one, and the other one is 0.09 something. So now if we just have a look at the MATLAB code is really easy because it's almost the same as for the last two sessions. So first we define the sampling time, then we define some sampling points. So here from 0 to the 40th sampled. We define our Z variable, so our Z variable using the transfer function toolbox. So it's a transfer function element. Then we can define H1 and H2. So H1 and H2 are the two transfer functions we found. So here it's written in positive power of Z, which is a little bit trickier to understand if there is a sample delay, whatever. So that's why I've been writing it into negative power of Z in the PowerPoint. But it's exactly the same denominator for the first and for the second one. Here it's not clear that it's the same denominator, because if we multiply this one by Z minus 1 on top and on bottom, we indeed find exactly the same denominator. Then we can find U of t, and we can find the first output. So here, the first output, I'm computing it with the first method I want to show you. And this first method is, first you define U in the t domain. So here U of t should have been written X of t because our input is X. So here it's a little typo from my side. Here it's X. So in MATLAB, it should be X here. So input in time domain should be called X, whatever. So we define the input in the time domain. We have our system as a transfer function system, and we have our time. And when you have all of these, you can directly use the LSIM command in MATLAB. I don't remember if we've seen it already, but never mind. Using LSIM, you only need the system, can be continuous or discrete, and then you need the input in the time domain and the time domain signal, so the reference time. So here it's just constant sampling time, such as 1, 2, 3, and so on. But whatever, this t should match the ut. Okay, so u is the input at each t value. And so this LSIM command works both for continuous and discrete time system. Then the second method is first to use the input into the z domain. So here our inputs in the z domain should be called once again x of z instead of u of z. It's z minus 5 minus z to the power 5 minus z to the power 5 minus z to the power 4. So here it's another way of writing it. But if we look in the code, this is just what we found in the PowerPoint. So it's just one step at t equals 0 and one step at t equals z to the minus 4. So it's z minus 1, z to the 1 times z minus 4. So it's the starting at the 5th sample, basically. And here we use the Dirac. So we create a Dirac. Here the Dirac is nothing else. If I just plot it with respect to t, it's not properly speaking a Dirac, because a Dirac should have an infinite value for the first sample, but it's just 1 for the first sample and then it's 0. So I should have written it this way instead. So the first at t equals 0, it's 1, and everywhere else it's 0. So it's equivalent to a Dirac with not a finite value for the first sample. And now we can use once again the LSIM command, but here a little bit differently. We first compute h2 of z times u of z. So this is the z transfer function, basically, or the output in the z domain, sorry. And we compute the Dirac of it, so the impulse response of this, which is strictly speaking equivalent to using the first method here. So here, just write a little bit. So the first method we have here, we said that we have, so I'm going to write it with u, but in the PowerPoint it's x, but never mind, u usually denotes the input. So we have, let's call it y equals, was it h times u, okay? And so if we have h of z and u of t, then we can use this comment here, this one here. In this method here, let's say we have h times u, but here we know h of z and u of z. And if we know h of z and u of z, we cannot, sometimes it's not easy to translate u of z into u of t. That's why I'm showing this second method that looks a little bit strange at the beginning, but it's only good point of this method is if you don't know how to translate u of z into u of t. Then what you can say that y of z is h of z times capital U of z, okay? And so this will be a z domain output, and we want to find the time domain output. So to find the time domain output, we can say by extension of this that y of kt is equal to the step response. So be the step, no, sorry, not the step, the impulse response. Let me just clear this one. Never mind. The impulse response of this system. Okay, so the impulse response of this system in the z domain is y of kt. So if you don't know how y of kt can be expressed, u of z, sorry, can be expressed as u of t, you can use this second method. And then you can plot everything, or we can plot everything, but it's exactly the same as what we had in the PowerPoint. Just remove all the comments. So here we can see the first system is the yellow one. The first system is, so the legend is not working because it was already something in the figure. Let me just do it again. So the first system is the blue one, and second system is the orange one. And we can see that if we add, for this specific system only, if we add a sampler between the first, so J1 and J2, our system output, let's say, is faster and has a little bit of a higher gain, which is, I mean, it's almost impossible to say that just looking at the system in the block diagram. But if you use a little bit of the computation we've seen today, or just look at the system output response, we can see that adding a sampler will make the system faster. Okay, so now, do you have any question regarding what I've just been talking about? So adding the sampler, the reference transfer function, the difference between here, the two system we've been working with, a question about the MATLAB code or whatever, or is everything clear for you? So if everything is clear, we can move to the first question for the, I don't know, sorry, first we have to find the pulse transfer function. So we want to find the transfer function of the disturbance of the input this time in the Z domain, but removing the input sampler. So here are our two systems, system 1 and system 2. And now we just say that here there's no more sampling and here there's no more sampling. The question is, can you find a transfer function in the Z domain so that the output Z of Z is a transfer function times X of Z? Obviously, for the first system, you can conduct all the analysis in continuous time, but here we want J of Z, okay, as something times Z. So the output Z of Z times J of Z times X of Z. So we're not interested in the continuous time domain response here. So for the first system now, Z of S is G1 J2 times X. So it's just continuous time domain equation, really simple to understand. And then we discretize it. And if we discretize it, we come to a problem, which is we have to discretize all the elements that are coupled, let's say, to each other, because there's no sample here, no sample here. So I cannot say X star of something times something. I have to, I mean, X is always attached to J1 and J2. So here you can see that it's impossible to split the terms. So it's impossible to get this equation here because J of Z is coupled with X of Z. So it's impossible to find a transfer function. If we look for the second system, it's more or less the same. We have Y of S star. So Y of S star, it's our intermediate signal here, is just J1 times X of S star because it's once again no sampler here, so X cannot be decoupled from J1. And then we take the output star, so the discretized output Z of S star, so Z of Z, and we say it's J2 times Y star. Y star is known, J2 is known. We discretized everything, Y is already discretized. So we end up with J2 star times J1X star. And here, exactly the same problem, we cannot find J of Z as Z of Z divided by X of Z, because this time X is coupled to J1. So remember that when there is no sampling of the inputs, so here the input is X, when there's no sampling here, and X is in continuous time, then it's impossible to find a transfer function expression like this one, so classical transfer function expression of the sampled output. So still it's possible to compute the continuous output here, no problem, but the discrete output as a function of the discrete input, there's no relation that we can found. So it is also clear that the sampling input is really important. It was also covered in the lecture. So if it's still not fully clear, you can just have a look at the slides again and also in the lecture. So now let's move to the first question. So the first question of today is we consider the following system with a zero order holds here. So it's just a sampler if you prefer, so just taking one sample and then holding the value, followed by a plan G. So plan G here can be expressed in continuous time, discrete time, whatever. And then the question is to find the only true statement. So only one possible correct answer. So answer A is that knowing U of KT, so U of KT will be equivalent to U star in the T domain, in the time domain, and the continuous system, so you know an expression for the continuous plant, then you can find Y of T, so the continuous output. The second proposition is that knowing U in the Z domain, so knowing U in the Z domain means that you know U star in the Z domain, knowing that the plant can be expressed as J of Z, okay, you can also find the output in the time domain, in the continuous time domain. Second proposition is that knowing U here, so directly the continuous U in the time domain and the plant in the discrete domain, so J of Z, then you can find the continuous output. And the last answer or proposition in that in all the cases, it is impossible to find Y of T, so Y in the continuous domain, but you can only find Y star of KT. So you can only find the discrete or the discretized output. So let me just open another poll. Here should be this one. And please take time to consider this question and try to find the only correct answer. There's only one answer that is correct. Also, remember what we've been talking about, and the answer is probably not that easy to find. If I just can give a little bit of a hint. 40% said answer B, 40% said answer D, and 10% said answer C, and someone is completely lost. Okay. So if I show you, so first, before showing the correct answer, it's not answer B. Can someone explain why answer B is wrong? I mean, we've already seen that in the previous sessions. So why is B not a correct answer? Can someone try to say something or explain it very quickly?
I think we can only guess what YT really looks like, because we we can only sample it in a discrete time, but we can't know for sure in the continuous time domain what YT is doing, because like maybe in between sampling times it did something that we did not expect, or something like this.
Yeah. So you're right. So I've already done that before. We can find U of Z and J of Z are in discrete time. So we can definitely say that here, I can put it here, that Y star or Y of Z, let's call it Y of Z, is J of Z times U of Z, no problem. So from this, we can compute the inverse Z transform and find Y of KT. And so we'll end up with some points like this, let's say. And exactly as you mentioned, we can try to guess what's in between. So here we can say that probably the output is this, but also probably the output is just something like this, which is completely different. So that's why the second answer was not correct. Now the third answer, so knowing U of T and J of Z, one can find Y of T. This is also wrong for exactly the same reason. From U of T, you can easily compute U star because you just need to sample it. And we know that sampling is just taking one value at each sample time. So quite easy to do. And then you can find U of Z and J of Z, or U of KT and J of Z with the method we've seen before, and compute once again Y of KT. So first Y of Z and then Y of KT. And so the third answer is exactly the same. It's exactly the same proof that it's not possible to find Y of T, is that you don't know what's happening between the samples. Then the last answer was also wrong. So the last answer was wrong. The only way to show that it was wrong is to prove that this one is correct. So can anyone guess why the first answer is correct? And the first answer, I guess, you've already all been working in continuous time analysis. And so if we put it differently, and this is really important, it's not because we're talking about discrete system or you see a sampler in somewhere that the continuous rules or continuous method you've seen before are not valid anymore. So you should be really careful. It's not because there's a sampling or a sampler or zero the whole somewhere that everything is discrete and I can just use something of Z everywhere and I can only find the discrete outputs. Here's the first answer says, you know U star, okay, U of KT. You know J of S. So in the continuous domain, you cannot find Y. So in the continuous domain, so here it's only in the continuous domain. I can say that, I'll put it differently, I'll put it capital Y. So I can say that Y of S, and you all know this, is nothing else than J of S, okay, times the inputs in the S domain. So let's call it U star in the S domain, okay? Now, you all agree that if I can find U star in the S domain, I can perfectly compute YS, and then from YS, I can say that Y of T is the Laplace transform, the inverse Laplace transform of Y of S. It is clear for everyone that if this is known, then I can compute Y of T as for any regular continuous time domain system. So it is clear. If this is clear, then the question is, what is U star of S? And if you just have a look at U star, so just gonna remove everything here. U star, question is what it is. U star is U that is sampled, but we don't really care because in the first proposition, we directly know U of KT. So if you know U of KT, that means that the signal, if I just write U of KT here and here the time, then I will have a bunch of samples. Okay, so T, 2T, 3T, and so on. And U of KT is just some points like this, right? Then the question is, what is U star? And here U star is perfectly, we can define U star in the continuous domain because the only difference between U of KT here and U star is that we've got a sampler. So the sampler here, or the zero or the whole here, is just holding the value. So here I can write it in red. that this signal here, which is a continuous signal, it's not, I mean, it's in continuous time, so it's not, the first derivative is probably not continuous, it's obviously not continuous, but still, this signal U star here is perfectly defined in the S domain. It's just one step, another step, and so on. So if I want to write U star would just be a sum of step function, like this, step of t minus something, okay? So U star is just U, kt, which is whole. And so if I know this signal in red, then I can just apply the continuous rules that you all know and find Y in the continuous time. Okay, so Y in the continuous time in this case will just be the output for each segment here. So each segment can be considered as a step, the input step. And so for each input, I can find the relevant output with the right initial conditions, okay? So is this clear that A here was the correct answer and why it was correct? So the real important point here is that it's not because there is a sampler that I cannot use continuous rules anymore, okay? So always ask yourself, do I know the signal? Do I know the signal in continuous time, discrete time? And sometimes knowing it in discrete time, you can find it in continuous time because if it's a sampler in between, what's between the point is known. It's just the value that is held or held. Okay, so if this is clear, we can move to the second exercise. So is there any question? So now we can move to the second exercise. So just stop sharing the results. So now let's go to second exercise. So second exercise is almost the same. We're gonna look at the reference transfer function, and we're also going to look at the disturbance transfer function. So here we got our sampler here, because we know that without the sampler, we cannot find the reference transfer function in the discrete time domain. And the first question is to find the closed loop reference transfer function. So here, talking about closed loop transfer function. So for the closed loop transfer function, it's exactly the same as in continuous time. We have our reference, which is called now omega, and our output is Y. So if I just compute Y in the S domain, as usual, in continuous time, you have Y of S is J of S times the input of J of S. And the input J of S is this signal here. We're looking here, I haven't said it, but at the reference transfer function, it's entitled. So we define that, or we set Z to 0. So the output Y is just J times H0 times U star, okay? So here we can also see that Y of S cannot be found because it's a function also of U star of T. So cannot be found in the Z domain, okay? Then we can look at U star. So what is U star? U star is just sampling value here of the output of the controller. So it's JD star times E star, okay? So E here is already sampled because we know that we need to sample the input. And so finally, what is E? So E is here is just the reference minus the feedback, so minus 1. So we can say that E in the continuous domain E of S is omega S minus Y of S. And if we sampled it, it's the input sampled minus the output sample. Now, if we look at Y of S, we can just replace here in the expression U star. So we can say that U star is GD star times omega star minus GD star once again times Y star. And if we replace everything, put GD star at the beginning because it's written here, it's a gain, it's a unit gain. So usually we put the gain before everything else. We end up with this expression, okay? So we got Y on the left, we got Y on the right, but on the right it's sampled and on the left it's not. So once again, we need to sample everything to make it consistent. And if we sampled everything, we end up with this term here, H0 times J of S, that cannot be, I mean, you cannot split H0 and J of S. You need to sample both at the same time, basically. So we've already seen that this is equivalent to finding J of Z from J of S with zero order hold method. We just need to compute H 0 times J and sample everything. And so from this, we can put this minus Y here on the left-hand side, and we then divide it on the right-hand side again. So we have Y star minus, Y star plus GD star times H0G on the left-hand side, and then we divide everything on the left and on the right, and we end up with this expression here. So this expression here is nothing else than the closed loop transfer function where H0J of Z are the term that cannot be decoupled from one another. And we can call it J omega, so Y of Z is J omega of Z times omega of Z. Now we can have a look at the disturbance transfer function. So the disturbance Z transfer function, this time we consider that omega is 0, and it's more or less the same. We can find Y of S, so Y of S is G of Z times G times Z. So this is just this loop here, J in the Z domain times JZ in the Z domain times Z, plus everything here. Everything here is not 0 because omega is 0, but the output also is used, and the output is for sure not 0. So we need to remove this GD star H0 GY star, which come from this equation here. Come from this equation here when omega is 0. Okay, we've already computed it. And so now you can star everything, so you can discretize everything. And if you discretize everything, you see that there's a problem because here you cannot split all these terms. They're all expressed in the S domain. So there's a mistake, should be Z of S here. Never mind. And so if you just want to find, as here, Y of Z is a function of something of Z divide, a transfer function in the Z domain time Z of Z this time, then you can see that there's a problem. It's not possible because when you Z transform all this expression here, you need to Z transform everything at once. So you cannot say that this is the Z transform of J of Z times J times the Z transform of Z, but you need to Z transform everything. So here, just we make the correction so that it's fully clear. Here it's Z of S. And so when you transform everything in the Z domain, everything here is coupled. So we can see that the closed loop for the reference and disturbance transfer function are exactly the same. This is exactly the same as in continuous time domain. And we can see that here's the numerator. We've got kind of a problem. We cannot express this disturbance transfer function as regular Y over Z equals something because Z is coupled in with the transfer function itself. So this is happening just because I've got no sampler here. If here I just add a sampler or a zero order hold or a sampler, whatever. So here I've got Z, then I just sample it like this and then I plug it in. Then if I had this sampler, I will have no problem here. Here I will be able to decouple everything. But usually the disturbance is not known and the disturbance is in continuous time. You cannot really sample the disturbance because usually it's happening inside the system. It's not like an input basically. So now we can look at the reference transfer function. So here it's what we found and we can, so reference transfer function is just Y over omega and we can compute it. So to compute it, we need to compute this term here, GDZ H0J, which is the same on the numerator and part of the denominator. So J of this is just a gain. It's a gain of the controller, so no problem. Then we need to compute the Z transform of this expression using a zero order hold. So you remember, we need to multiply by 1 minus Z minus 1 and divide the system by 1 over S, okay? So you can find it here on the right-hand side. H0 is 1 minus exponential minus TS over S, which turns out to be 1 minus Z minus 1 over S, okay? And you also remember that when you Z transform two expression, you cannot split this expression unless it's just a unit delay or any delay basically. So here we got a delay of 0 sample and a delay of 1 sample. So we can split everything accordingly. If we compute this, so we need to find the partial fraction decomposition. So 1 over s times s minus 3 should be equal to a over s plus a. And using the inverse Z transform table, if we look for this expression here, a over s plus a. So where is my Z transform table? It's the fifth one you see here. So you got a over s plus a. Here, it's 1 minus exponential minus 80. So here, you have two options to compute it, whether you use partial fraction decomposition and you will find a step and an exponential decay, whether, as proposed here, you directly identify this term and find everything at once. Okay, so it's just a kind of a shortcut, but both methods will be exactly, will lead to exactly the same answer. So if I go back to the PowerPoint, whether you use partial fraction decomposition as usual and you will find one step and one exponential decay, whether you directly identify this form here. So if you want to identify this, here you have minus 3, here you have 1, so it doesn't work, so you need to add again. And if you add again of 1 minus 1/3, then this here is equivalent to minus 1/3 times minus 3 divided by s minus 3. And so from this, you can directly find this expression. So it's kind of a shortcut instead of using the partial fraction decomposition and then multiplying each term together. So we find j of d of z times h0 j of z, which is multiplied by the gain of the controller, which is 10. So here, nothing special. And then knowing that the sampling time is, I don't remember, but the sampling time was given. We just have a second. So sampling time is 0.03 here. So given the sample time is 0.03 second, we can just find the numerical application for this reference transfer function. And so the reference transfer function is this term here. So this one here, you can see that it's here and there. So here you can just use MATLAB. It's a little bit easier to do than doing it by hand. And if you plug this term here inside the transfer function, then you find this approximation. Also, you can do everything in, let's say, using a symbolic toolbox, for example, you can use or find the analytical solution. So analytical solution is just taking this value here and plugging in here, and then making some simplification. And you can find j omega, whether with the parameters. So here parameter is t, or just a numerical approximation if t is given. So here, I guess there's not a lot of new things. It's more or less like in continuous time, and also what we've seen before for this, computing the Z transform of a signal with zero order hold. So we can have a look at MATLAB. So the MATLAB code is pretty straightforward. We've already seen it. So we define the sampling time t, 0.03. We define z and s, our variable in the discrete and continuous time frequency representation. Then we find that the planned transfer function is given in the continuous time, sorry. The jz of s, this is, I don't remember which one this one is. This is, sorry, the disturbance transfer function. It's also given in the continuous time. And finally, we have our zero order hold, which is 1 minus exponential minus ts over s. Then we can find j0 of z. So j0 of z is this expression here that appears on top and on bottom. So I just call it j0. It's the open loop transfer function if you prefer. And then you can, from this open loop transfer function, find the closed loop transfer function and evaluate it into MATLAB. And you have exactly what's written in the PowerPoint, okay? So here using so not replacing t or putting t as a variable instead of one value, you can find also this expression if you want using a symbolic toolbox, for example. So now that we have the transfer function of the disturbance reference transfer function, we can compute what the output y should look like when there's a step in the disturbance. So it's Once again, not a step, but just a combination of two steps. So it's like one step and then it stops. So disturbance transfer function, we know that this JD H0J of Z is known, so we've already computed it. And there's a problem. The problem is, if we want to do it in discrete time, we have a problem because we cannot split the disturbance Z from J of Z and J. We need to Z transform everything at once. So that means that we need to consider the Z or the disturbance, we need to consider it into the S domain and then transform it along with J of Z and J all at once. So the disturbance in the time domain is just tensored of a step function minus another step function. So you all know that in continuous time, step function is 1 over S. We keep the gain, the static gain, and then we just add a shift. So a shift of one sample or a shift of any time, sorry, because when in continuous time is written as a negative exponential. And then from here, we can identify that 0.3, it's equivalent to 0.3 over t because t is 0.03, okay? So here we're just kind of matching here or expressing this time delay into a number of sample delay. So this is just a delay, and this is a delay of 0, so I can put it outside of the Z transform, and I can Z transform everything else. So everything else is just the disturbance transfer function, the Planck transfer function, and 1 over S, which is coming from the disturbance expression. If I compute this, I can use partial fraction expansion. Once again, it's in continuous time. Then you can identify simple terms in continuous time and directly find it using the table in the discrete time domain. So here we mostly have this S minus something and 1 over S. So 1 over S is its step function, and 1 over S plus something is an exponential decay. So if we just have a look here, but we've already seen it a couple of times, 1 over S is a step function, so it's 1 over 1 minus Z minus 1, and 1 over S plus A is an exponential decay. And we also perfectly know an exponential decay can be written with this form. So here, just classical step, you can just have a look at home if you want to do it again. And finally, we can compute the output. So the output here is approximately equal because there's a lot of decimals for all the terms. I haven't computed the analytical output because it's not required, and it's probably going to be quite a big equation that's not really interesting for us. So here we can just use this function here or this expression here. And as we've already seen, even if MATLAB is sometimes making some approximation for the exponential, it should be perfectly okay to use it. So if we just have a look at the MATLAB code here, nothing difficult, we just define Z in the Z domain directly here. Then we find JZJS. So this term here is everything that needs to be Z transformed, okay? It's everything in this parenthesis here. So everything I need to Z transform. I also included the gain, but the gain can just be completely ignored, so it's not really important. No, indeed, I did not include the gain, but you can include the gain if you want. And then I'm using the symbolic toolbox. So symbolic toolbox is used to compute the partial fraction expansion, remember? Here I got the expression for this partial fraction expansion. So it's 1 over S plus something, 1 over S plus something, and 1 over S. So it's a step and 2 exponential decay. And then I can compute this J of Z times J times Z. And this expression here is nothing else than the open loop here, or almost the open loop because it's a disturbance. So we cannot talk about the open loop, but it's just this term here, okay? Then I can multiply it by Z. So I'm just multiplying the numerator by the expression of the disturbance in the Z domain. And finally, I can compute the output. So the output is the numerator. So it's the numerator of the transfer function times the disturbance in the Z domain divided by 1 plus J0Z, which is the denominator we've already computed. So if I run everything, I can find the output. So the output is this one. So here it's the output in the Z domain. Now, if I move on, I can draw the output, what the output looks like. So this is what the output looks like. So we have our disturbance. So our disturbance is just here. So it's a set of points here. So it's a step until the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe 10 or 11 time step. And then there's another step so that it reaches 0. So disturbance is only acting on the beginning, at the beginning of the system. And in black, you can find y of kt. So this is my y of kt. And there's something quite interesting that's here. If you just scroll to the right, at one point, this is happening. So the disturbance is always 0. I can also show it in MATLAB. Done a second. So if I just plot it in MATLAB, it will be a little bit easier to visualize that at the beginning, it's completely fine. So if I just plot the output until 2 seconds, it looks like the output is completely bounded and then go back to 0 because the disturbance is 0. But indeed, if I just scroll to the right at one point, so the disturbance here is always 0. At one point, you see that the output is starting to be negative. And so that will be the second question today. Here it is. Why is the output going to infinity, or in this case, minus infinity? So I'm going to start another poll. Should be this one. So also take some time to try to figure it out why this is happening, why it's going to minus infinity after, I can show it here. It's like from 10 seconds, the output just goes mad to minus infinity. Why is this happening? So please take time to enter the poll. As usual, it's anonymous, and here there's multiple choice, so multiple correct answers. So I'm just gonna let you a little, some seconds or some minutes to answer this one. So almost 64%, so not everyone answered that MATLAB is making numerical approximation. This is true, and we're gonna see that in a second, but here it's not directly linked to the approximation of MATLAB. I mean, it is, but it's not that easy to see it or to visualize it with just the information that are provided here. Some poles of the reference transfer function are outside of the unit circle. So this is true. Can someone explain why this second answer was true? Why? Because the reference transfer function is unstable, this one is also unstable. And the answer is exactly the same in continuous time. So the answer is, if I go a little bit back, let me just go back a little bit. So before everything here, it was here. Here, if you remember, cannot stop it now. So exercise 2. In this slide here, we've been computing all the transfer functions, so reference transfer function and disturbance transfer function. And if you remember, they have exactly the same denominator, okay? So you can see that the denominator of the reference transfer function is the same as the denominator of the disturbance transfer function. So in continuous time and discrete time, this is always true when you have this form of system, let's say. So you have the open loop of the reference transfer function, then the closed loop, and the disturbance is just acting here, and the closed loop is taken from the output. And this is a classical block diagram representation. Then the disturbance transfer function always has the same poles at the reference transfer function. And here it's true that if the system or if the transfer function is not stable, then the output is not bounded. So this is why we have this negative input after quite some while, is because there is one pole that is outside of the unit circle. Then the third answer was the disturbance transfer function is not stable. This is also true. I just explained it. So one of the pole is outside of the unit circle. At least one of the pole is outside of the unit circle, and so it's not stable. And the last answer was only a continuous disturbance can be compensated. This is not true here. I mean, the disturbance transfer function here we've considered is indeed continuous. If you remember on the previous slide, here it's written there that Z is already continuous. So we are already considering that Z is in continuous time domain. So this last answer is just not right at all and cannot be right at all, basically. So here, there is one pole outside of the unit circle. But now what can be interesting to look for is why is this happening only after like almost 10 seconds? And when this is happening like this, after quite, I mean, it's always at 0, and then at one point it starts to be unstable. It's probably because one pole is really close to 1, 0. So here, if we just investigate this, with the next slide, we can look at the poles and the zeros of this transfer function, the system. Remove this. So we have 15 poles and 14 zeros, okay? And this is because MATLAB is making some approximations. And so you can see, for example, that there's 11 poles at 0 and 2 zeros at 0, and MATLAB is not removing the poles and zeros that are at 0. So here what we can do is remove 2 poles at 0 and remove the 2 zeros at 0, because you know that one pole can compensate a 0. Also, so this is not really important. If you don't do it, the transfer function is a little bit more complex. It's 2 degrees higher in the numerator and denominator, but it's perfectly fine because these poles are completely stable. The problem is for the 2 other poles here and zeros here. So at 1 and approximately 1.09. So the one at 1 is stable. Our system is not asymptotically stable, but it's marginally stable. That means there's some kind of integration behavior. So we should also remove it if we can. And here there's the exact same poles and zeros at these 2 locations. So once again, we can remove those poles and zeros. So if we do everything, we end up with only 11 poles. So we removed 2 poles here and the 2 poles which are here. And the zeros are only the zeros everywhere else. So we don't really care. They're on the unit circle, one is here, and that's all. And so now we have a stable disturbance response because the transfer function has all the roots of the denominator of the transfer function are inside the unit circle, okay? So the answer of the question that I've been asking before is that the transfer function was unstable, but this is coming from the fact that MATLAB is not able to perfectly remove the poles and zeros which are located at really, really close location. So if we just look on MATLAB and we just draw the root locus, am I drawing it somewhere? So I can draw it here. So our function is, transfer function is this one. I haven't computed it, so never mind. If we draw the root locus of this, so of the transfer function, so it's our numerator divided by our denominator. What's happening? Oh, okay. This one is symbolic toolbox, so it will not work. I thought I was working it, so never mind. We're gonna look at the, so here, not relevant right now. Is it probably here, everything? So I haven't said, if you draw the root locus, basically, so you need to define everything using the transfer function toolbox and not the symbolic toolbox. That one I cannot do it here. You can zoom in here and you will find that the pole and zero are not exactly matching each other. But I just checked it yesterday, and this pole, for example, at 1.09, as it is not exactly located at the same zero, but there's 1 to the power minus 5 difference. So 1 power minus 5 difference is really, really small, and you can assume that the pole is compensated by the zero. So if you do that, if you do all these compensations, so you remove these 2 unstable poles and 2 unstable zeros, then you can see on this graph that the blue signal here is exactly the same as the black signal. Basically, the black signal is just hidden behind. And this time, if you just scroll to the right, the black signal is still unstable. It's the one from the beginning, and the blue signal is perfectly stable. So on MATLAB, to do this, what you can do is first here, you're going to define a variable that is the poles that you want to remove. And so you're going to look at all the poles of your system. So here's the poles are given here. So if I just plug that in, here are all the poles of our system. They're already, I need first to recompute all the poles because they've already been simplified. So now if I look again at all the poles, you can see that there is one pole here that is unstable and another pole here that is marginally stable. And if you look at the zeros of the function of the transfer function, so zeros are here, you can also see that you got exactly the same zero and exactly the same pole, zero here as the pole. So one at 1 and one at 1.0942. Still, if you look, for example, if we take this one, so it's the third one. So if we take the third one, and for the pole, it's the 1, 2, 3, 4. Is it the 12th or 13? The 12th one. So if I plug this minus the zero at the same location, or what looks to be the same location, you see that I've got the difference for this one of 1 to the power minus 14, okay? For the other one, if I remember well, it's 1 to the power minus 5. So when you've got this, that means that it's quite likely that the zero and the pole are exactly at the same location, and so you can remove it. And so this is what these functions here are doing. There, you can just look at it at home. I would share the code on TUVEL. Basically, you're just looking at all the poles, all the zeros, and if one zero is sufficiently close to a pole, then you remove this pole and this zero. And once you've done this, as already done before, then the poles at 1 and 1.09 are removed, and the zeros at 1 and 1.09 are removed. Okay. And so this is the output. So the output is, if I just put remove equals to 1 once again. Oh, no, sorry, it's not this one. It is this one. So I changed something. Anyway, it should work. I will make it work basically, but you will end up with this graph here where you can see that the new system, so the one with the removed poles that are unstable, is showing exactly the same output as the one in black. So the original one at the beginning, and at the end, it's remains stable. So is there any question regarding this, once again, a kind of approximation problem in MATLAB? It is really important to consider because a lot of time you will find some transfer functions that are perfectly stable, but because there is some poles that are not fully compensated by MATLAB because it's just a little bit offset from the zero, then you can end up with an unstable transfer function. So now we can look at the second question for today. So when computing the closed loop preference transfer function of a discrete system, which statement is false. So this time, what is the not correct statement? So if you want to find the closed loop reference transfer function, you should ignore the disturbance. Answer B, all the closed loop poles should not coincide with any closed loop zero. C, it is impossible if the input is not sampled. And answer D, one should consider all signals as being sampled. So here there's one of these propositions is not correct. The three other are perfectly correct. And I would just ask you to try to guess which one is not correct. Just launching the poll. So now you have the poll. So which is the false statement among A, B, C, or D? It's a single, only one statement is wrong. So the correct answer, most of you answered the answer D, and it was indeed the correct answer. We've seen it before. We can never say that everything is sampled, okay? It can be true, we can sample everything, but most of the time, or I mean, at least it's possible that some signals cannot be sampled or are not sampled in our system. So this is the correct answer. Now, if we quickly have a look at the first answer that nobody chose, one should ignore the disturbance. This is true. If you're looking for the reference transfer function, you consider Z 0. If you're looking for the disturbance transfer function, you just consider that the input is 0, exactly the same as in continuous time. The second answer, we've just seen it just before. If any closed loop pole is, so coincide means it's sufficiently close to 0, that means that one or this pole is compensating the 0 and the 0 is compensating the pole. So we can just remove both of them. And answer C was, it is impossible if the input is not sampled. We've also seen that in exercise 1. If you do not sample the input, you cannot find the transfer function written as the output in the Z domain is equal to some transfer function of Z times the input in the Z domain, okay? So is there any question regarding first exercise and second exercise and this question? There's no question anyway, we can move to the conclusion and then you can further ask some questions thereafter. So conclusion for today, we've seen, we started from continuous system and using zero order hole and sampling, we were able to find the discrete reference transfer function and the discrete disturbance transfer function. Remember, only when the input is sampled. Then we were able to find the output in the Z domain, no problem. And sometimes also the output in the T domain. So output in the T domain, usually it's Y of KT only. And sometimes we've seen it in the first question, you can also find Y of T directly. And obviously we need to make sure that MATLAB is not skipping any pole zero cancellation. So we should just have quickly look at the root locus or just all the numerical values for the pole and zeros and see if one is matching another, then we should cancel these and pole and zero, okay? So now, is there any question regarding this second session? Or also question regarding session 1 and 2? I can still answer any question if you have some.